Thanks a lot, Alejandro, for the kind introduction, and of course also thanks to everybody involved in putting together this nice program, Anna, Ash, and Derek. It's a great pleasure for me to be here and speak to you about the work that we do at the Max Planck Institute of Quantum Optics, where I work as a group leader. So the title of the presentation is Quantum Optical Switches in Ordered Atomic Arrays. It's slightly changed from what I had originally submitted, because I actually wanted, in addition to what I can say about our work on quantum optical switches that I will introduce, also include some newer results, preliminary results on a different type of switch system that we looked at MPQ. I will also give you, hopefully in the end, a brief overview of some ongoing projects that may be interesting to simulate discussions with everybody who's here. And I'm, of course, very happy to discuss with everyone. So let me start basically by motivating our work on ordered atomic arrays. Basically, the idea here is coming from this sort of fundamental problem of interfacing light and matter. If you think about a single atom that you try to interface with a light beam in free space, that the probability for that atom to interact with a light beam is limited, and it's limited because the cross-section of the atom, which of course is proportional to lambda squared, divided by the area down to which you can focus a light beam in free space, is always smaller than 1, significantly smaller than 1. So you have actually to do something in order to improve and to enlarge this interaction probability. And there have been a couple of ways discussed in the literature. Of course, also a lot of work been done in this direction. For example, using just more atoms to get a higher probability of having interactions between light mode and atoms. So here, of course, the optical depth increases, so you get a higher chance of having an effect and interaction. You can also use an optical cavity, place the atom inside the optical cavity, and then have a photon run around multiple times and give it a higher chance to interact with the atom. So this is, of course, the field of cavity QED. Or you can use a nanophotonic device. You can constrain the mode of the light field to volumes that are smaller than what is possible in free space, and by that enhance the interaction between light and matter. What I will be talking about towards the end is our efforts on building cavity QED systems where we put single atoms inside cavities like shown here. But most of the talk, especially the beginning, will actually be focused on our efforts to realize strong light-matter coupling in free space by actually not using disordered atomic arrays, but actually ordering the atomic ensemble and then letting the light field interact with an ordered atomic array. And in particular, what is interesting, or where this becomes very interesting, is if the distance between the atoms in this ordered atomic array is smaller than the wavelength of light. And I will be explaining to you how we can actually realize such systems, how we can probe them, and also how we can control them using the control we can have over the individual atoms in this array. So here's the outline of the talk. Yeah. So I will first introduce this concept of cooperative atomic arrays. That's of course been discussed a lot recently, and I will tell you how we can control those with individual atoms. Then I will actually tell you how we can use ideas that we developed in the context of controlling these arrays, translate this to controlling spin systems. So this is new work. And then I will give you a brief glimpse into a new project that we're setting up at MPQ, a new experiment where the idea is to couple atom arrays to cavity QEDs, or to a cavity, so to do cavity QED with individually controllable atoms. All right, so let me start from the basics. So first of all, let me introduce our experimental platform. So the experimental platform we have in our lab is a so-called quantum gas microscope. So what is a quantum gas microscope? Well, it's, as the name implies, the main part here is a very good microscope, and we can actually use that microscope to look at individual quantum systems that we prepare in 2 dimensions. So we have here various optical lattices, in particular a vertical optical lattice where we can isolate a single slice, and we can put a degenerate gas of rubidium atoms inside the single slice. In addition, we actually have control over the horizontal axes. We also have optical lattices here, which allows us to, for example, generate systems where we have dilute distributions of atoms. So you see here, this is a typical image we can capture with this microscope, where every white dot here indicates a lattice site, and you can see that some sites are occupied by atoms. This is indicated by a high level of fluorescence from that site, and other sites are empty. What we can also do is we can actually use the control we have over the system to realize very dense systems, and in particular we can use the techniques that have been developed in the context of generating or making Bose-Einstein condensates to drive this two-dimensional system into a Bose-Einstein condensate, and then via control over the optical lattices to a mod insulator, where the special feature that we are going to make use of here a lot is that in this mod insulator we know that per latticite we have precisely one atom. And this is, of course, a very nice realization of such an array, because these optical lattices, if you look at the distance here between two laticites, are smaller than the wavelength. We have exactly one atom per side, so this is exactly an ordered atomic array like the one I was showing you. By now, we actually were able to push the numbers of atoms that we can put here in these mod insulators above 1,000. This requires then also some potential shaping. It's not so important for what I'm going to show you here, just as a side remark. All right, so let me start also at the basics when talking about ordered atomic arrays. So what's the idea of these ordered atomic arrays? Well, first of all, let's consider a single atom. So of course we know when we drive a single atom, we induce a dipole. In this case we are assuming a weak drive, and the dipole will radiate. So in order to calculate the total field of this configuration, you have to basically take all contributions of the external drive plus the light field radiated by the dipole and add those up. And of course, in order to get the light field of the dipole, you have to use the Green's functions of the dipole of the single atom here. So for a single atom, this is very straightforward to do. It becomes slightly more difficult if you add a second atom, in particular if you add a second atom that is close to the first atom. So what happens here is that basically, in addition to considering the effect of a single atom alone, you also have to consider the effect that the electric field generated by this, or light field generated by this one atom, also of course affects the dipole of the second atom, and vice versa. So in the end, what you have to do is you have to find a self-consistent solution for this system, where you take into account exactly this influence of one atom to the other, and in the end, this gives rise, if you solve for the dipole pattern in the self-consistent way, to collective modes that we're interested in. Two interesting or famous collective modes are, of course, the modes where you place these atoms very close to one another, and you can either have them oscillate in phase, then you would have a super-radiant mode, or you have them oscillate out of phase, and you have a sub-radiant mode. If you start separating, some of these features survive, but the picture is slightly modified. In the end, I already mentioned this, if you want to get the scattered field, what you do is you just take the pattern, the dipole pattern that you obtain from this analysis, and you add it on top of the electric field that you drive the system with, and you can get the full field distribution from the contribution of the scattered field plus the drive field. So in other words, you can calculate very well what's going on in the system, at least in this weak excitation regime. So this is the situation for two atoms. One can also look at the situation for many atoms. Actually, the pointer has a delay for whatever reason. Maybe there's some interference. Okay, I don't know what this is. You can also calculate what's going on for many atoms, and for many atoms, in the end, the picture is analogous. So rather than having modes, like two modes here, what you get is you get many modes, you get many collective modes. Typically, because we are considering here for many atoms and an ordered atomic array periodic systems, you would label these with quasi-momenta Q, and you get a line width typically associated with this collective mode, and also an energy or a detuning. And what we can ask then is, what happens if we now take such an array that has these collective modes, we take a Gaussian beam that we have access to in free space, and we ask for the response of this array to shining in this Gaussian beam. And we can look at the response both in terms of the line width of the system, like how the overall system responds with respect to its line width, and also what's the energy of the collective mode. And this is exactly what's shown here as a function of the distance of the atoms in this array divided by the wavelength. And maybe we can start here at very short distances. What you see here is that the line width at these very short distances actually becomes much larger than the natural line width, and this is exactly, of course, the super radiant regime where you have a stimulation effect basically of the presence of the atoms or the close the vicinity of the atoms. Then what you see as you bring the atoms apart, this super radiant effect at some point changes to a subradiant effect, and then whenever you hit the right wavelength, for example here at distance, for example here at distance corresponding to the wavelength, the system can strongly respond again, and this is a very characteristic response fingerprint, so to say, of this ordered atomic array. You also see that the collective modes have a dependence, an energy dependence here, or this response has an energy dependence, so you see actually line shifts depending on the distance of the array. Now, for the experiment that we are concerned with, this quantum gas microscope, our spacing over lambda is actually about 0.67. So basically, our mod insulator that I was showing you before is sitting here. So it's in an interesting regime where the line width that we would expect actually to see when we probe the system is below the natural line width. So it's a subradiant configuration, and the energy shift is close to 0. One thing that is important, and this is actually also why these systems are very interesting as light matter interfaces, is that in particular in the regime below the where the spacing is below the wavelength, there's actually no diffraction orders possible just from classical grating physics. You know that if you shine light into a grating and the spacing is smaller than lambda, then the only order that survives is the 0 order. So what that means is actually that you can actually send, in principle, all of the light back exactly into the mode that you excited from. There's like no diffraction into other modes. And this is actually something that was figured out in 2017 here by Effie Shamoun, and also in the group of Stuart Adams pretty much at the same time. So what they looked at is actually how this response of the array in this weakly driven regime is if you shine in a Gaussian beam, and they found that if you set your the tuning correct, you drive exactly the correct mode, that you can actually basically have perfect reflection from these arrays. And this is, again, up to a distance between the individual emitters that is equal to the wavelength. And similarly, you see this here in these results. So here you find for a specific configuration a point where the transmission goes down. Actually, here they considered a slightly different geometry. This is a square array, this is a hexagonal array, and in principle, or triangular array, in principle, the feature survives. So it's not so important what exactly the configuration is, as long as it's ordered and it's below the wavelength of light. So this is basically the light story. Of course, there's also an interesting meta story, and I think this is in particular interesting if you leave this weak excitation regime. So in the weak excitation regime, a lot of the calculations that you can do here are classical, but if you leave the weak excitation regime and you look at the spin model that is involved here, so thinking about the atom as a two-level system, then of course this has very interesting many-body physics, and that's very nice work by Anna here from 2017, and also more recent work, for example, looking at fully inverted systems and then looking at the cascade, how these inverted systems can actually decay, and what is expected here is actually a super radiant burst of the system as the system goes from this highly excited state down sort of the ladder. So this is very interesting also from a many-body physics perspective, and very difficult to describe because it's an open distributive many-body system. All right, so so much for the theory. Let's look at an experiment. So how can we probe the physics of this array? Well, this is actually for us rather simple because the way I set it up, I explained to you we have this ordered atomic array and we have a Gaussian mode, and we can expect what the response is, so we can just basically see if we can reproduce the response that we expect. And there are basically two ways in which we can probe this array. So first of all, of course, we prepare this mod insulator, and then we can either probe the response of the array in transmission, or we can probe it in reflection. And the two cases are shown here. So if we probe in transmission, what we expect is that this beam is strongly attenuated because we expect this to become a very good mirror, as I said, for the correct detuning. Whereas if we probe it in reflection, we expect to see very strong reflection. And then what we can do is we can just vary the probe detuning, so we basically see if we can see the dependence of the response on detuning. And you see here typical curves that we record. So this is just the transmission measurement, and here's the reflection measurement. And you can see, interestingly, that what we measure is a response where the line width of the measured feature is below the natural line width. So the natural line width, the natural response is this Lorentzian given with this dashed line, and we measure something that's smaller. And so this subradiant feature is actually the first indication that something very interesting is going on, and it's actually consistent with this calculation that we can do for the system. So in this regime that we are in, we expect a subradiant response. You can also actually think about from the reflectivity, from the reflectance here, you can think about what you expect if you had just a disordered array, and actually for disordered array, the expected reflectance would be just 0.2. So you can see this boost in reflectance is actually also an indication that here we have a cooperative response of the full system. One can also quantify this. There's a nice work by Effie Shamoun, co-workers, where they show that a reflectance of 0.6, if you translate this to sort of a cooperativity parameter, this would correspond to a cooperativity of the system of about 4. And cooperativity in this sense is the quantifies the ratio between controlled and uncontrolled sort of emission. So how much of the light is coming back into the mode that you can control versus how much of the light is actually going into uncontrolled channels. So this is, if you compare this to cavity QED systems, actually quite a decent cooperativity in the system that we have here at hand. All right, so this is all, if you want, linear optics, right? We send in a light field that is a coherent state, and we get a coherent state back. What I now want to talk about is how we can control this, and also how we can actually go from a linear optical response to a nonlinear optical response. First, I will explain how we control our system with the atomic degrees of freedom that we have control over. And of course, what I should do before going to our work is I should give credit to the large amount of work that was done in this direction. So what's the main idea here is that in addition to the two-level response that we want to use here, we actually exploit strong atomic interactions. And strong atomic interactions have been used in quantum optical systems for a long time before, namely using strong Rydberg interaction between two atoms, and then connecting that with two-level response. And the main technique that has been used here, pioneered in the group of Misha Lukin and Vladan Vuletic, is to actually set up an EIT scheme where you couple the two-level system that is your optical two-level system that is optically active to a Rydberg state to set up an EIT condition, and then you make use of the strong Rydberg interactions to break this EIT condition to modify how the light then couples to the optically active two-level system. This has actually been developed for almost a decade or more, and it's of course ongoing, this field. I just want to highlight some nice sort of highlights, in my opinion, that came out of this. So here is a work from Gerhard Rempe's group, where they actually put such a system, quantum optical system, inside an optical cavity, and they were actually able to realize quite good photon-photon gate, in the sense that the efficiency with which this worked, I think, is the highest. At least was at the date where this was done. These interactions have also been used in the meantime for other purposes, for example, to detect Rydberg atoms. So here's a nice work from Vladan Vuletic's group, where they used this strong Rydberg interaction to detect the presence of a Rydberg atom. All right, so we want to basically follow the ideas developed here for these disordered quantum optical systems and translate them to our array. So how do we do that? Well, first of all, we start with our array, where the distance between the atoms is smaller than lambda, and this is just characterized by the simple two-level response. We probe the system here actually in a time scale that is shorter than the Rydberg lifetime, which will be relevant in a second. What we do then is very simply, we just turn on another light field here on top of our two-level response that couples to a Rydberg state. And of course, by that, what we generate is we generate an EIT or Outlier-Towns doublet, where the splitting between these two resultant lines is given by the coupling strength of this upper transition here. What we also do by doing that, actually, and this is crucial, is because we are coupling to the Rydberg state, of course, we are also introducing Rydberg character and therefore also sensitivity to Rydberg interactions into these Outlier-Towns doublets. And this is now actually key, because what we can do now is we can actually select one of the atoms and use that to control the response of the other atoms. And how do we do that? Well, we can selectively and in a controlled way excite this one atom, in this case to a different Rydberg state, and the presence of this Rydberg state will actually then modify the behavior of the atoms all around because of this strong Rydberg interaction between this state R prime and the admixture in the Outlier-Towns doublet on the rest of the mirror atoms. And so in how we do that in the experiment is we basically, in a controlled way, before the actual mirror probing experiment, excite this ancilla, and by that we can then actually modify this response. And this response occurs because EIT breaks down and the system within this blockade radius goes back to a standard two-level response, like before. This is an idea that actually was also brought up, and I think pretty much pioneered by the Lukin group, in particular Rivka Beckenstein here, where they actually described how one can actually use this combination of ordered atomic arrays together with this Rydberg control for a variety of applications. I think I just put on a list. This is quite interesting because compared to these three-dimensional systems, these disordered arrays, there are quite some advantages of this ordered atomic array if you use Rydberg control, because basically you have very good control over the loss of the atoms, right? In this three-dimensional cloud, because of the disorder, there's always some degree of uncontrolled scatter, and this is actually strongly suppressed in this ordered atomic array. And then there are a variety of applications that follow from that. What is of course also interesting is the multi-mode character that we have here in the system. You can think of this array as basically with multiple ancillas as controlling multiple modes locally, spatially of the light. And so this is, I think, a unique feature of this system. So very interesting perspectives if we can make this work. All right. How does now our experiment look? Well, it's very simple. It's exactly repeating the steps in the experiment that I was showing you conceptually before. So first of all, we set up our standard mirror response. Again, this is a subradiant response. It's the same distance, same spacing as before. And the only thing we have to actually make sure is that we can actually get the same signal to noise that we got in our first result, in our first work, but during a lifetime of the Rydberg ancilla, because of course in the end we want to be able to switch with the ancilla, and so of course the switch only works if the ancilla is excited. The Rydberg states have decay times of a few 10 microseconds, so everything now has to happen on a shorter time scale. But that's more experimental concern, not so much conceptual concern. Next, we basically just add EIT, so we turn on our coupling light, and here you see the resulting doublet. So now we have set up everything we need in order to switch, and of course the switching behavior is now expected to go from this strong reflectance to this transmitting behavior, or vice versa actually. Here's what happens if we add the ancilla. So we now just select a single atom in the center of the array, and we then perform this mirror probing, and you see in the red trace here the effect. It's exactly what we expect. So starting from our EIT spectrum, we actually regain some of the reflectance, reflecting behavior of the array due to the strong Rydberg-Rydberg interaction. And what I should say in the end, actually what we see here is a superposition of these two curves, and the reason we see a superposition is twofold. So first of all, our preparation of the ancilla is not perfect, and of course whenever we don't perfectly prepare the ancilla, we would still see the EIT feature. And second, there can actually still be instances where the ancilla decays before we can probe the system, and so the system actually switches back from a reflecting behavior to a transmitting behavior during the probing. And these are our current imperfections. So here's what this looks spatially. So first of all, we start setting up our mirror here. This is basically corresponding to the absorption of this mirror in probing in absorption. Then we turn on EIT, so the system becomes transparent, and then you can see here the switching volume, where in the center we put the ancilla, and then within a certain radius, the blockade radius of the system, the mirror changes actually its properties. What we can, of course, also do is we can then use the control we have over the ancilla, for example, driving Rabi oscillations. So here you see Rabi oscillations measured via the ancilla, and look at what happens when we try to probe this with the mirror, and this is the corresponding data in transmission and also in reflection. You basically see that the switching of the ancilla, or the Rabi oscillations of the ancilla directly translate to the reflectance or the transmittance of the mirror. And this is, of course, a nice proof that whatever you do on the ancilla is directly mirrored on the ancilla. Again, here you see actually looking at the reflectance, the comparison with a disordered system that we do experimentally, and you can see that you still get this cooperative response if you excite the ancilla, so do a pi pulse on the ancilla. All right. There's actually also an interesting point here in the in when you actually put the ancilla in a superposition, and this is of course also a lot of the toolbox that was explained or brought forward in this work by Rydberg Beckenstein and also Misha Lukin, which says, okay, if you have control over an ancilla, you can put it in a superposition. You can in principle also put the response of the mirror in a superposition. So in other words, you can realize spin photon entanglement or entanglement between the ancilla state and the reflectance or transmittance of the photon wave packet. And so this is an interesting point to look at. So far we actually have not been able to show the entanglement, but what we can do in our experiment is we can actually post-select our data of reflectance or transmittance based on the measured ancilla values. And if you look at this here, so 0 atoms means actually that we detected the ancilla in the state where it was in the Rydberg state, because effectively we lose it after some time. And so here you see a clearly enhanced reflectance, which is exactly what you expect. And similarly, if we don't detect the ancilla, so if the ancilla was in the ground state after the experiment, then the reflectance is actually lower than expected. So it's exactly the right trend, but of course it's not yet showing any entanglement. It's just showing a correlation that is interesting. And of course, it would be cool to see this and probe this entanglement in the end and see whether it's actually there. All right, very briefly about the limitations. So what are our current limits on the system? So first of all, on the mirror itself, this is also true for our non-switched mirror. We are actually at the moment limited by the positional uncertainty of our atoms. So they are sitting in a lattice. The lattice has a finite wave packet size. And so this is limiting the reflectance that we can have. We can unfortunately not make the wave packet more tight. Why not? Because the lattice that we use is not magic. This means if we make it the lattice deeper, then we will actually get additional heating sources, and that actually reduces our absorbance. So this is also not an option. For both of these, we actually have a solution, which is to add a magic lattice. In this case, we could magic meaning the motional, the excited state is trapped in the same way as the ground state. So there we can just make the lattice much more deep, avoid this heating effect, and then also mitigate the problem of the positional spread. And the second thing that we have, this is connected with the ancilla lifetime, is a rather short ancilla lifetime. So here what we can do is we can just, in principle, reduce the probing time significantly, such that we are not so much limited by the decay of the ancilla. This upgrade to a magic lattice is actually ongoing right now. I wish I could show you some data, but we don't have it yet, but it's coming soon. If these solutions don't help, what else can we do? Well, we can go to different elements. For example, we have a strontium machine here at MPQ that is mostly focusing on quantum simulation, but I think this could also be quite interesting in the context of these quantum optics experiments. Let me briefly give you the idea of this experiment. It's basically a lattice-tweezer hybrid. We have a large-scale optical lattice where we can trap and image individual strontium atoms, and we can also use our tweezers to control the strontium atoms. One thing that we've done very recently is we've realized these ordered arrays, basically not via some mod installator physics or anything, but just loading the atoms essentially in a lattice like this, and then using a single tweezer to sort them, and we can get to these large arrays. You can see they are not yet perfect, but we're working on improving them, and this will be possible. And what is interesting in particular in strontium is that then the level structure of strontium, because in addition to the ground state, there's also this metastable manifold. In particular, the 3p2 excited state has a very long wavelength transition to the 3d3 state, which is closed. So this could be a very good candidate in the end to do these quantum optical experiments. And here, just to give you an idea, if you compare the distance in this lattice here that we saw to the wavelength, so this is actually the distance of the atoms that you see here, to the wavelength of these 2.9 micron, then here we are at 0.3, and this is actually quite, should give quite much more strong effects than what we have in the other lattice, where this is a factor of 2 larger. And so we are, at the moment, working towards getting this set up. There's a small experimental problem with this transition, which is that there's water resonances close by, and so the first thing we have to check is whether these water resonance will actually prevent us from getting this light into our experimental glass cell. So this is something that we have to check. And if the answer to that is we can do it, then this would be super exciting to follow on. Very briefly, let me show you these new results on this Rydberg spin switch. So the idea here is actually borrowing a lot of the ideas that I already presented to you, so I can actually be quick on the conceptual points. So in this mirror, as I said, we have an ancilla and then a quantum optical system that we control via this ancilla. what we want to do now, or that idea we had now, is actually, well, why can't we just sort of swap the roles here for sort of technical reasons? We now say, okay, our 2-photon transition here that we used before to realize the EIT, we now use it as an ancilla, and we just use it as an ancilla by doing an off-resonant 2-photon excitation to the Rydberg state. And we then combine this with a spin system, where now the admixture that we realized here in this EIT scheme, we realize it via off-resonant Rydberg dressing. And the idea is now that we can actually use this ancilla in the same way where we control the switch here to actually control the spins in this Rydberg dress configuration. What we have to do in order to do that is we actually have to sandwich we have to actually find a way in which we can get sort of a effect on the spin system, and the way we do that is actually in a Raman Ramsey interferometer that we realized using a Raman system. And let me briefly walk you through this idea. So the idea is very simple. So first of all, we look at the case where, in this case, we have no ancilla. We just set up a Rydberg dressing regime. So we Rydberg dressing setup. So we basically couple the ground state to the Rydberg state. This is our prime state. What we expect here is then that the system picks up an AC Stark shift if we sandwich it into this Ramsey interferometer. So the spins will precess. And then if we then add an ancilla into the Rydberg state, due to the same Rydberg-Rydberg interaction that switched our mirror, we will actually increase the detuning here to this, that gives rise to this light shift, and this increased detuning will actually then lead to a much smaller spin precession frequency because the light shift decreases. So the idea is very similar, it's just translating this mirror idea onto the spins. And here's basically our experimental result. I should say this is all very preliminary, and we're still trying to understand what's going on. So here are our Ramsey oscillations, our spin precession basically without the presence of the ancilla. You see this nice AC Stark shift. And this is basically consistent also with the expectation that we have. Just a few numbers. We work here with the Rydberg detuning for the dressing of 40 megahertz, which gives rise to an AC Stark shift of about 600 kilohertz, taking into account all the MJ states in the system. What we do now is we just excite the ancilla into the Rydberg state on this 2-photon transition. And what you can see here is actually you see that now the system actually still oscillates, but the oscillation amplitude is quite strongly suppressed. And we can actually understand that. So to some extent, at least to what we would expect based on the numbers, is actually that the Stark shift reduces because of this additional detuning due to the interaction to something like a tenth or so of the value when we don't have this ancilla present. So we would actually expect a much smaller oscillation frequency, and this is actually the reason why we see the strong reduction in contrast. However, we still see this oscillation at the original frequency, and this actually for the same reason as I explained in the case of the quantum optical switch, is actually can be traced back pretty well quantitatively to the imperfect preparation of the ancilla. So whenever we don't actually put the ancilla, the system will still respond with this full amplitude, and in the end, you actually have a superposition of both cases. But I would say the working principle here is demonstrated, and in the end, what we have to do now is we have to improve the preparation. Similar to the quantum optical switch, we can of course now think about using this spin imprint, this phase imprint, to detect the presence of the ancilla, and this is shown here for the case of detecting Rabi oscillations. So we can either measure this directly again on the ancilla, this is the orange trace, or via the conditional spin shift on the target atoms in this Ramsey interferometer, and you see basically perfect agreement without adopting any parameters. Interestingly, we can now also go and use our control over the position of the atoms to measure the switching volume that we have here. So we prepared 3 different configurations here with the atoms separated at different distances, and then we can see how this switching behavior depends. So this is just the contrast of this oscillation, and you can see actually, if you look at that for various distances, a very good agreement between the expected shifting based on the Rydberg interaction between the ancilla and the spin and what we can measure. And interestingly here, we can actually, from these data, conclude that in principle we can put up to 25 atoms or so within the switching volume. So with one ancilla, we can actually control the spin state condition on that ancilla of about 25 atoms. All right, so in the last few minutes, I will talk about some new developments we do in the group to basically set up a cavity QED experiment with atom arrays. So let me very briefly give you the motivation for this. The motivation actually originally is on a quantum information side. So the idea here is basically to be able to have individually controllable atoms that we can actually combine or control with the toolbox we have for Rydberg atoms, for example, to do digital operations like gates with local control that we have, for example, to control the state of individual atoms, and this optical resonator for readout of the states. And one of the ideas is that what we want to do is we want to basically, taking all of these things together, realize, for example, a logical qubit inside this cavity by using the entangling gates between the atoms to set up, for example, surface code, and then using local control to read out individual atoms for stabilizer readout. The way you can do local control, there are various ways in which you can get local control in the cavity. One is actually by coupling to higher excited states, or one could also basically put the surface code next to the cavity and then move in individual atoms. So this is ongoing. It's an experiment that is being developed right now. I just want to give you a brief update on what's going on. So first of all, we have our first cavity characterized. The cavity parameters look pretty promising. This is preliminary, I should say. So everything is in principle in vacuum, but we have to verify that these systems are correct, these numbers are correct. But we are hopeful that we can get maybe this as the most important parameter, a cooperativity of something like 10, I would say. But this is to be verified, maybe it could be slightly smaller. For the Rydberg excitation, we are actually planning to do a UV excitation because that's supposedly good, for example, to get you very high Rabi frequencies. And of course, we can also play these tricks that I showed you before with the Rydberg dressing and kind of combine some of the physics that we've already explored also in this new setup. The status here is basically that we have the system working together. We have our cavity in this glass cell sitting there. We also have a cloud of cold rubidium atoms. And very recently we added our objective. And at the moment we're actually preparing the individual atoms inside the cavity. We haven't found a signal yet, but we are very confident that we are very close. So in principle, all of the steps should be pretty straightforward. We also found our Rydberg resonance on the mod. So I think the things are coming together. And I think we are quite excited to get all of these bits and pieces together. A very brief word, just also to stimulate maybe some discussions on what I think is interesting. I already mentioned about the setup. I already mentioned basically this direction of quantum error correction that we want to go into. I think this, however, is also very generally interesting, for example, to do quantum simulation of open systems, combining this cavity as a degree of openness into this spin system, for example, via Rydberg dressing that I was mentioning. And of course, it's also super interesting, I think, to consider what one can do on the, say, more traditional quantum optics side. For example, there's this very nice work from the Rydberg group where they, with a similar setup with just two atoms, were actually able to build quite impressive photonic many-body states. And I think it could be very interesting to think about how one can actually adapt the toolbox that I presented to sort of go in a similar direction. We also do other things in the lab. I didn't have too much time to talk about this, and I want to gloss over this. If you're interested in any of these topics, like extended Hubbard model, Hilbert space fragmentation, exotic Rydberg molecules, or quantum computing with Rydberg atoms, please come to me, and I'd be happy to discuss. Most importantly, I should, of course, thank the team. So most of the switch work was actually done by Kate here, both on the quantum optical side and also on the Rydberg side, and then also, of course, the teams working on the strontium setup and on the cavity setups who are putting a lot of effort in making these systems work. And I think it's going to be exciting to see what's coming out. With this, I'm at the end. I want to finish leaving up the conclusion, and I'm happy to take your questions.
Thanks a lot, Johannes. I was feeling bad of taking the time because yesterday I was encouraging you to put more things. But anyway, so thanks a lot. So now it's open for discussions. Yes, Kanu? Yeah. Maybe use the microphone because it's recorded.
Thanks for the very nice talk. This is all very exciting. About the correlation measurements that you mentioned in the case where the ancilla was in a superposition, what exactly are you measuring in that case?
So basically we can do two measurements. So we can first of all measure the optical response, and then after the measurement we can also check the state of the ancilla. And then what we can correlate is we can correlate the outcome of the ancilla measurement with the measurement of the optical response. So in the one case it's just measuring whether an atom is there or not, and because we lose the ancilla if it's in the Rydberg state, and the other case is basically just counting the photons in the region of interest. Those are the two things that we calculate, and then we can correlate the two.
So just a follow-up to that. So because in this case you have a entanglement between whether the field is reflected and transmitted and the state of the ancilla, can you do some measurements on the ancilla and then interference of the fields to see whether this was indeed an entangled state and how coherent it was?
So we haven't, so in principle one can think about this. I think it's going to be challenging for us to do this. What we can do is we can basically put this ancilla in a superposition, measure the optical reflection, and then do another operation on the ancilla, another pi over 2 power. So this we can in principle do, and then we could see what's coming out. I think in general, but maybe this would be something to discuss. It's very challenging, I guess, for us to see this, for example, to realize a Bell state, which you could think about using the scheme, because in the end what we would have to do is we would have to erase the which way information of the photons. So we'd somehow have to overlap the two paths that the photons can take in the end, to basically avoid that the system gets somehow projected that way. And I think this is in principle thinkable in our experiment very hard. Yeah. So one would need a dedicated experimental setup.
I see. Thanks.
Yes, we have another one.
Hi, Johannes. Thanks a lot. Very nice talk. So my question is about the switch. So you just go for one single Rydberg excitation, if I got it right.
Right.
But in principle, you could have a lot of the Rydberg excited state and start to go not about control, but about many body effects.
Yes.
So to my understanding, this correlated emission business is very well understood the level of few excitations, but when you go into many body, there is no idea what's going on.
A good question. So I actually didn't explain this at all, but one thing we actually have to make sure when we set up this EIT scheme is that we don't drive the system too strongly. Forgetting about the ancilla. So just setting up the Rydberg EIT. Because if we start driving the system strongly, we'll get what's called self-blockade. It's actually the idea of all the, a lot of the quantum optical experiments that have been done in bulk with Rydbergs. Because if you crank up the probe power, you'll actually start enhancing the probability to find more than sort of one Rydberg excitation in the system already. And that actually will then lead to a nonlinear effect on the mirror response itself, even independent of the ancilla, and we've actually looked at that. In this case, we try to avoid it because we don't want that. We want a linear response unless we put the ancilla. But we have looked at actually it's here. Yeah? We have looked at the nonlinear response. So if you start driving the system very strongly, you go actually, this is without ancilla, you go from ATS doublet back to the reflectance just because you're starting to saturate the system and you get a strong nonlinearity just sort of self-generated. I think this is interesting. Actually, we still don't understand fully at a quantitative level ab initio what's going on here. We are working with people. I've discussed with, for example, Thomas Pohler, also Effie, about understanding this. But I would say this is still ongoing and not very clear. I mean, we have the data, so if you are interested, let me know.
Okay, so I have one question. No, but yes, Hannah. Yes.
Thanks for the talk. Regarding the action as a mirror, maybe I missed it, but did you look at the non-linear response simply due to saturation? I would suspect that the reflected light is just coherent light with a flat G2.
Yes.
Whereas if you look behind your array, you should see bunched light. Did you see something of that kind?
So we did not look at the photon statistics yet because we cannot. So this is all done with an EMCCD actually, because that's the way the experiment is set up right now. It would be awesome to have a single photon sensitive device so that we could actually look at the correlations. Everything that we did on the mirror was actually intentionally in the linear regimes, on the weak drive regime. In principle, we could crank up the probe power, which in principle should also get us into a regime where we should see nonlinear saturation effects. However, in practice, this is not so easy because the more photons we scatter, the higher the probability that we actually lose the atom. So this will actually reduce the filling of the mirror, and then there are other effects that sort of mix into this. So two answers. So no, we have not looked at that because we cannot. We have looked at the saturating behavior, but it would be very nice to look at that more quantitatively with a single photon sensitive device. Yeah.
But just one comment. I think that this effect is independent of the saturation. Okay, so you do not need to crank up the power, but even in the linear regime, you see nonlinear transmission in the sense that everything that goes through, no matter how low the saturation is photon pairs. It's bunched light.
Okay, that's very interesting. Yeah, we haven't looked at that, but because we cannot, but I think it would be very interesting.
Okay,
I have to think about it. Yeah, thanks.
Mm-hmm. Okay, so maybe to keep up with the schedule. So I saved my question for the coffee break. So let's thank Johannes again. So I think the coffee break is now on the left, in this courtyard, and we come back in half an hour.